Let's continue on. Today is March 8th, 2017. Let's continue on to yesterday's extreme battery trilogy. This is the second part. To the nano equipment, a combination of nano motion and high temperature sintering. So really what we said about yesterday talking about the processing ambient to get the highest volume of a storage density. And however, if we want to reach the lowest resistance of carrier movement, that is, we talked about the boundaries, the green boundaries of. So here is a picture of this is the SEM scanning electron microscope picture. So very general. It's just a fracture surface of the processing is 900 degrees C under the nitrogen ambient. If you look at the scale bar here, this is 6 micrometers, 6 micron. So if you look at the grain size it's estimated about a few microns size, the domain size of a crystal. In a piece of a crystal, if you at this micro crystal structure, so you really have a tremendous amount of boundaries, right? We said before, in the abstract, charging and discharging resistance in the material may be controlled by crystal domain size or green boundary density. 20 years ago, I read a paper. It claims when a metal crystal size reaches nanometer level, a metal wire or cable will not be a conductor, it will be an insulator. I think it is easy to understand. A charging or discharging process really is a process of charge carrier movement with orientation in the battery materials. Major resistance comes from green boundaries. If inside of a crystal material or in the way of a carrier movement does not have any boundary, the resistance is minimized. Then that means the charging and discharging speed are maximized. And also if the resistance minimized, that means you will not lose more energy. So because when you have the charging, discharging, if the resistance, inner resistance is higher, then you will generate unavailable work, right? That will, convert the energy into heat or something else. Then therefore the lower the maximized resistance, that means unavailable work is minimized. But how to make the whole complete single crystal, that means in the way of carrier movement, there's no boundaries. How do we make that? How could we make it happen? When I started think a way to make a nanometer diameter whole complete silicon carbide single crystal fiber, I started think the process and the possible equipment. Then I recalled a few years ago when I was a CTO of a technology startup. For some reason, I participated a consortium conference at the University of Colorado at Boulder. I met the COO of then, it was a local startup company called Nanomotion. Nanomotion. It might later be acquired by a larger corporate. The nanometer movement control may be popular anyway, so in any case, really is, but I'm not the one to make the automation of nano movement. So many people can do, so some researchers in EE or, some people making the automation. I can make the mechanical, actually physical movement. I cannot make the electronic control, but that's not important. That's really means the application, how do you combine, how do you direct the nanomotion to some real applications. At that time I don't know what they are doing with nanomotion to work with on what application. At that time I did not find a connection between my application and this approach until I figured complete crystal processing. It's really, the thinking is a nanomotion stepping induction furnace at high temperature operation. That is the combination to combine the nanomotion stepping into the induction furnace. The induction furnace really, that allows you to control you target the hot zone to some specific location on the examples, then it won't heat up somewhere else inside of the furnace. So if you can control the slowly move the in the nano motion stepping to control the speed, the hot zone to move from one location to the other. That is the thinking. That will allow a high temperature zone slow moving from one end to the other end of a piece of a target material. And then it allows an epitaxy process to a complete single crystal. That is the equipment part. So if you have that, you want to do some processing. If you don't have equipment, then you cannot do anything to the, for your purpose. So then the third part is the third part of the presentation is nano epitaxy. Epitaxy, a lot of people know what is that, right? The crystal grow on some seeds, then it's, extended to larger. So But nano, why we call nano epitaxy, it's really associated with the process. How do you make the whole complete piece of crystal? So if you sinter a whole piece of material and cool it down, what will happen is a nanocrystal seeds forms simultaneously anywhere in the material. That means you have many, million, billion, whatever. So each seed grows a nano or microcrystalline. So what we saw before, the picture that's micro scale, right? It's a microcrystalline. The domain size of a crystal is about a few microns. So if we don't want that happen, we don't want the boundaries of the green boundaries of a crystalline. So that you see the domain size is at nano or micrometer level, then you have a tremendous amount of boundaries. Sinter a material to a temperature higher than its melting point from one location, from one end of the material. You just heat up the locally, then you slowly move the hot zone. At the high temperature zone, move out of the edge. The seed or seeds forms on the edge plane. So you may not be able to make the whole complete single crystal, but you might be able to make the columnar, structures. So you see it forms from one end when that move out. The hot zone moved out. The seeds, the crystal will grow from the seeds and on the way toward the direction to the other end. That means you might be able to make the complete columnar crystal, complete single crystal, so that means on the carrier movement direction, the direction for carrier movement, you don't meet the crystal boundaries, right? So that's the thing. You have the process ambient to control to reach the maximum volume of carrier storage density to the upper limit by still keep your single crystal structure, and you have the equipment allows you to do the process of nano epitaxy. Then you have the stepping to the processing steps to make the no boundary in the way of carrier movement, right? That's whole thing to make something happen. You can reach the maximum storage, and you can reach the charging discharging speed and the lower resistance, right? And the energy efficiency. I would like to say, really is not to, the seminar is not to prove something, really is to say, do something others did not do yet, right? I really reviewed many papers in many topics, fields, many of them, 90% did the reflecting the maybe reflecting repeated work of others. Of course, you quote in your reference, you quote the references because you cannot do everything. You may focus on one thing. However, when you quote many papers, you have to make sure you really believe or you have a confidence what the papers said. Some papers really did give the solid evidences to solid evidence to make you have the confidence, okay, I believe that. And some of them probably, I don't know, even the writer, the authors, they really believe that. Do they have the confidence? The same thing, really, I mentioned before for example, the neutron diffraction. So actually, if you did something really great, for example, some breakthrough in science or something, do you want to share, right? So really, definitely, sometimes you may have the conflict of interest or some other regulations. However, what I'm trying to say is do something you are the best and let other people do their best. So then, for example, if you make a great material, some characterization you might not be able to do, but if you just let other people to do, right? So who did the better or the best job in the characterization, or if you did very great a characterization nobody else in the world at that moment can do. So you may want to also, in a consortium, what is a consortium, the efficient consortium, that topic I will talk about later in other seminars. That means, so as in a talk show or a comedic cameo joking, say, oh, if something everyone can do, I'd rather do something no human beings can do, right? Of course, it's a joke, but it means something that you don't want to do something many people can do. You want to do something really great, your best, right? Thank you. If you have a video seminars, if you have a video seminars, I really would like to watch, right? If you want to share. So my next seminars are Systematic Life Science, Challenge the Ultimate of Life, Review Milestones of Umbilical Cord Blood, Umbilical Cord Tissue Transplantation, Billing Questions. Then the next one, Mistaken Concept of a Material, Extremity or Perfection of a Graphene and Carbon Nanotube. The next, Mistaken Concept of VC. VC is a venture capital. Okay, of VC presentation of an executive summary from a scientific breakthrough to an entrepreneurship. Next, smart extreme materials and non-motion cryogenic equipment. Cryogenic equipment. Next, extreme fields, electric, magnetic, or others, and their applications. I present this using English and Chinese. Hopefully, I will be able to use Spanish, Russian, Portuguese, Japanese, German, French, and Arabic too. So really, I would like to use a more modern media, like live live video broadcasting and everything. It's really the medium currently a lot of different things. I would like to experience those things to share my thought, my experience, my questions with others. Hopefully you would like to. Thank you.